And now we are ready to look at the reactions of esters. So far, we have looked at the reactions of the acid chlorides, and we looked at the reactions of the acid anhydrides. And so now we're ready to move on to the reactions of the esters. And these, you're going to see, these are very similar. We do have one reaction that's different. Then this is the saponification reaction, as in making soap. This is the reaction that's used in soap making. So in this reaction, we're going to take an ester, and when we're making soap, we're using fats or oils as our source of the initial product, and fats and oils are esters, so they're serving as the ester in this reaction. This is a two-step reaction, so the first thing that you have to do is react the ester with a strong base, hydroxide, and then the second thing you have to do is react it with an acid, H3O+, which seems kind of silly that we're doing one right after the other, but we're going to look at the mechanism and you'll see why. So this produces a carboxylic acid, and it produces an alcohol also. I'll put a prime on that from the OR group of the ester. And so let's just take a look at how this reaction works. Most of the nucleophilic acyl substitution reactions that we're doing in this chapter, most of them are acid catalyzed, and this one is base catalyzed, so it's at least something different. So the first thing that happens is that OH group is going to attack the carbonyl carbon, and we're going to open up the carbon-oxygen double bond. It's going to be an O-. You've got your OR group on there. We've added an OH to it. And then what's going to happen next, and this part is kind of crazy, the carbon-oxygen double bond is going to close back up, and we're going to kick off OR as a leaving group, which is wild because that is a really, really, really strong base. And so it does not meet the criteria for being a good leaving group at all, but this reaction still works anyways, because it's driving itself towards a good product. So because that OR group is a super strong base and we've made a carboxylic acid, that strong base is going to grab the carboxylic acid's hydrogen and rip it right off, and we're going to get a deprotonated carboxylic acid. And we're also making, in that step, we're making an alcohol. And so that is the source of the formation of the alcohol. And if you've ever made soap at home, it does have kind of an alcohol-y smell as you're cooking it, as long as you haven't put a lot of fragrance in it. This right here is the soap. And so if you're doing soap making at home, this is where the reaction actually stops. But when we're doing this in the lab, like unless you're in the business of making soap, when we're doing this in the lab, we're usually trying to make the carboxylic acid. We're not trying to make soap. We're usually going for this guy right here. So that is why we need that step 2, where we add H3O+ to just go ahead and protonate and give us the carboxylic acid product that we're looking for right there. So this is where you would stop if you're making soap. So that's an interesting reaction of the esters. The rest of them are pretty much repeats of the stuff we've already seen. We have acid catalyzed, hydrolysis, which is ultimately giving us the same product as saponification reaction. We're just doing it with different conditions. So we're taking our ester, we're reacting it with H3O+, doesn't really matter what the acid is, and it is turning it into a carboxylic acid. We also have ammonolysis, which is going to be the same as what we saw for the acid chloride and for the anhydride. We are going to use NH3. We could use an H2R, we could use NHR2. We're going to get an amide out of it. We can do a reduction of an ester. This will give us an alcohol. We would do this with our hardcore, strong reducing agent, lithium aluminum hydride, followed by water or H3O plus. We do need excess lithium aluminum hydride for this reaction because we're going to need to add a few hydrogens, a few H minuses on there. When you're doing these reactions, be careful that you do not lose your carbonyl carbon. It's really easy to lose your carbonyl carbon. Just like we saw with the acid chloride and with the acid anhydride, if we want to, we can use a different reagent that's going to reduce us to the aldehyde instead of going all the way to the alcohol. So this one actually uses a different reagent than the acid chloride or the acid anhydride. Remember, with the acid chloride and the acid anhydride, we used that big, huge lithium aluminum triterpenoxyhydride giant thing. This uses diisobutyl aluminum hydride, which we abbreviate DIBAH, or you might see it written as DIBALH. And so this will stop the reduction at the aldehyde. The DIBAH is not a strong enough reducing agent to reduce an aldehyde. And then last but not least, we can react with a Grignard. And we have seen this Grignard reaction when we first learned about Grignards a long time ago. We do need, if we're reacting an ester with a Grignard, we need excess. I already have an R prime, so this is going to be an R double prime. R double prime MgBr. This is going to put 2 of the Grignard's R groups on the carbonyl carbon and also convert to an alcohol. So because we have excess, we're doing this reaction twice. We're putting 2 of the R groups from the Grignard onto the carbonyl carbon, and those are the reactions of the esters.